Thank you.
Shaila.
Thank you very much for your nice introduction for me. So yeah, so you big babies, secrets of star birth. These big babies are actually my babies, you can tell, because I work on high mass star formation. So I'd like to talk about who are those smart people I'm working with at the moment. So Dr. Maria Cunningham, she actually got the Outstanding Supervisor honor a couple of days back from our Postgraduate Research Council, which is a great honor. Dr. Lisa Harvey-Smith, she is from CSIRO. Dr. Paul Jones, he is also my co-supervisor, so I have 2 co-supervisors. Dr. Carmel Parcel, he is from University of Sydney. He is my advisor. Dr. Ali Nawaz, he just became doctor a day before, and he is my collaborator. And Dr. Andrew Walsh, he is the boss, actually, the project I'm working on. So he is also my collaborator from Curtin University. So what I'm doing in my PhD, so the research aims are to identify star-forming zones or clumps. I'll be going through all these jargons later on. Estimate their physical properties. So the star-forming zones, their molecular cloud is there, and how those molecular clouds form into stars. I'm identifying which zones are forming stars, and then estimate what sort of physical properties they have. Then modeling those clumps, some of them, compare those models with observations, understand the formation process of high mass stars. So why do I study about high mass stars? In general, stars can be of low mass star and high mass stars. Low mass stars are stars. If we think of our sun as solar mass, 1 solar mass, and we take the reference of it, so any stars having 8 to less than 8 solar mass of a star mass is called low mass stars. And anything with 8 to 20 times our solar mass, those big stars we are calling high mass stars. And so why this is important? Because their formation procedure is quite different than the low mass stars they form. And you can see here, there is a small, okay, this is nebula, which you cannot see really because of the darkness. So that's the nebula or the molecular cloud or the interstellar medium from where the protostar is forming. And that part is actually also for low mass stars. And when the protostars is forming, there is mass loss due to the outflow jets and solar wind, stellar wind. And then it becomes main sequence, then giant, supergiant. And before they become, this is the difference between a low mass and high mass star. High mass stars really fed up all their fuel so that they don't collapse into gravitationally, and they become supergiant, and then they become, some part becomes neutron star, and other of the mass, it recycles back in our molecular cloud or the space interstellar medium. And interstellar medium, I'll be talking more about that. It's a recycling process, and 20% of the mass come from this recycling process from massive stars or the high mass stars. So that's why they're so important. So in general, our galaxy, Milky Way, of course, we cannot really see our Milky Way galaxy in this way. It's an artist's impression. It is formed of stars, lots of stars, interstellar medium or the ISM, the jargon we use usually. It has got dust. It has got many other stuffs like some cosmic rays, dark matter, you can tell. But 10%, 10 to 15% of this galaxy is made up of interstellar medium. And that interstellar medium has got 1% dust. And other than that, 90%, around 90% is hydrogen, 10% is helium, and some other molecules it has got in interstellar medium. What other agents we have got in interstellar medium? Dust, cosmic ray particles, magnetic fields, radiation fields. The general temperature varies from 5 Kelvin to 1 million Kelvin. So you can see the variation. It depends on different places of the ISM. And density also varies from 1 atom per cubic centimeter to 10,000 atoms per cubic centimeter. So when we are talking about this variation, that means this temperature variation, we cannot really have the same temperature at all the places in the ISM. So we can have 3 different phases of the ISM. We have got cold phase, hot phase, and warm phase. To understand the cold phase, it has the temperature less than 100 degree Kelvin. It is the coldest part, densest part, and it's more molecular ions and inside it. Molecular, and then this is the main star forming zone. So not all the other part of interstellar medium form stars. Warm phase, the temperature is 6,000 to 1,000, 10,000, I think it should be, Kelvin. It is more diffused, ionized and atomic. And you can find this warm phase near our solar system, the neighborhood. And hot phase, the temperature is 3 million to 10 million Kelvin. Due to shocked gas, we can find this hot phase, and shocked gas are really very high temperature. And you can find this near the supernovae and newly born stars, which are really very hot. So how do this ISM, the interstellar medium, form? We know that it's gas and dust. In general, we know it. But how does it form? So I did give some of the information in this one, that it is actually forming when the protostars is forming from the ISM, it is forming, and then the jet is happening out, and then mass loss. That mass is coming back to the interstellar medium. Again, when it is dying out, after the death, some of the portion of the stars come back to ISM. So it's same thing here. So you have the molecular cloud or the interstellar medium, and then that is forming stars. During formation of the stars, it's losing some mass. And again, when it is dying, it is also returning back some interstellar medium back to space. And again, interstellar medium has a feedback to the intergalactic medium. So you can see how these high mass stars can shape our universe, our galaxy, and then our universe. So ISM has got atoms, molecules. I'll be talking more about molecular ISM, what molecules we have in interstellar medium. We have hydrogen, most of it is abundant, is hydrogen. We also have carbon monoxide, that's the next common one. But other key molecules, we have NH3, which is ammonia, my study matter, HCN, HCO+, HNC, and also other, we have got around 168 molecules that we have found until today. And it is like on, I think in every month we are finding 1 or 2 new complex molecules or new molecules in the interstellar medium. So I was talking about those molecules, but what do we do with those molecules? They're actually good tracer, so they can tell us particular story of the interstellar medium. And so this is very important for me to understand those molecules, to understand how the ISM is building up all those stars or is dying out. So you can see some of the molecules here. These are all ISM molecules, and they are emitting their frequency. They have this frequency, particular frequency for each of them, and they are tracing different physical parameters. So if I'm using N2H+, that means it's going to tell me that cloud density and it is chemically robust or not. Again, if you go for anything I pick, HCO+, again, it's talking about density. HCN, that's also talking about density. If you have found silicon oxide, that's talking about shock or outflow tracer. Outflow is nothing but how the mass is coming out from when the star is forming. So like jet or solar wind. So among all these ISM tracers, I'm using ammonia. And why? So you can see this nice molecular form. So this is really important to understand to see why am I using ammonia particularly. So ammonia has got 1 nitrogen and 3 hydrogen. And so this is the most ideal thermometer of the ISM. So it can be used for cold temperatures like 5 Kelvin, and it can be used for really high temperatures as well. Now, cold temperatures where carbon monoxide, carbon sulfide, all these molecules freeze out to dust, and you cannot really use those tracers, use those molecules as tracer for star formation, but you can still use ammonia. This is also a very good density calculator, and it is very important to understand the density of a molecular cloud, because from density you can tell if it has this much density, so it can form the star or not. Of course, the low density cloud cannot really form stars. And from knowing density and temperature, we can derive some other physical parameters like the mass, that it is gravitationally bound or not, that it can form a star, or is going to blow out and cannot really fragment, or is going to be fragmented, or is going to form a star or not. And also, this can be used as a better distance indicator. So what I look at ammonia? I look at the spectra of it. And do you know anything? So if I ask anyone what is a spectra, can anybody tell me? Yeah? What is a spectra?
The range of wavelength.
Range of wavelength. Okay. And versus intensity or something, right? No, that's a very good start. Yeah, but I'm really giving here velocity, right? That's really big fishy why I'm using it here. Okay, so you can derive velocity from the frequency or the wavelength. You know that wavelength and frequency just one inverse of another one, right? And we have got Doppler shift in the clouds. So they are actually moving around as well. They are not all the clouds are just static there. They are moving around. So they have got Doppler shift of their frequency or of their wavelength. And from that, you can calculate the velocity, which is V by C equals 1 minus F by F naught, where F naught is the rest frame frequency and F is the shifted frequency. So if you know those, you can actually calculate the velocity. And for this one, we are using radio telescope, so radio data. And the data comes as a 3D data cube. So position, velocity, that's the third exit. And the position is galactic longitude, latitude, and we know the velocity as well. So that's how we get the data. And I look at the spectra of them. So this is, nothing is written here because it's a normalized one. Usually you can put intensity. For my case, I use the brightness temperature. Looks very complicated, right? This one? This one looks complicated. Okay. How about, let me try to make it a bit easier for you. So I'm using ammonia 1-1 transition. So when we are talking about electronic structure, you know that it's like we all are electrons here, and we have got a building of 1, 2, 3, 4 levels we have got. Now, we can be in third floor or second floor or first floor or fourth floor, but not really in between, right? That's how the electrons have their own energy levels. They can have certain energy, and then they can jump up to the higher level, or they can emit certain energy, and they can jump down to the lower level. So we can do the same. So we can just climb down with the stairs or lift in particular level, and we cannot really go in the middle. But that's happen usually for atoms. Now for molecule, and basically I'm talking about ammonia, you can see these atoms are there, And with nitrogen, with hydrogen, they actually vibrate along this axis. Again, they are rotating as well. And they can flip around. So they can actually change their position around the nitrogen. And there is magnetic field as well. So all these things together, what they do, they split their energy level. So I have 1, 1, which is the first level I'm going, and that has been splitted due to spin first. So if you know the electrons have got spin, half is spin minus and half is spin plus. So that's called parity plus and parity minus. And that's going splitting here. And due to basic quadruple splitting, or the one I was talking about, that vibration, it is splitting again back into 3 different levels for ammonia. Again, each of them are splitting too due to magnetic hyperfine splitting. That's what we say. So magnetic field, they're splitting up again, and that's called hyperfine splitting. And now the electron, so it's like if so John is setting up a chair from there to here. So I can actually go up and sit down on that chair, right? So that's like splitting. So giving an extra level so that I can jump up to there. So I can have more frequencies. So all you can see this jumping, electrons can jump from 1 to 1, 1 to 2, 1 to 0, 2 to 2, 2 to 0, and all this sort of jumping from 1 to there, right? And from all this splitting as well. So if you look at from 1 to 1, 2 to 2, 0 to 0, all this splitting together, all those frequencies together, makes the main satellite, main line, main component, this component of ammonia. And these are called inner satellites. These 2 are called outer satellites. And those outer satellites and inner satellites you can get from all the other level jumping. So they are numbered here all. I'm not going through details because it's really quantum physics, and I can see a few people are actually sleeping. So I'll come back to become an astrochemist or astrophysicist. But for now, just for understanding the physics behind it, that's quantum mechanics and quantum physics. So you can see all those main jumping is making out the main line, and these numbers from other level to level jumping, they are making other 4 satellites. And this is making our ammonia 1-1 transition very unique. So this spectra you cannot find from any other ammonia, from any molecule, I'm sorry. Again, there is 2-2 transition as well. The difference is those satellite lines are further than the main line, and their intensity is lower than ammonia 1-1. And they have a particular ratio as well. Usually it is 26%. All those 4 fingers are 26% of the main one. I know it can remind you the root finger. I'm sorry for that, but that's how we remember it. Okay, so I have been talking about ammonia molecule. Now, how can I find this ammonia molecule? For this, I have got HOPS data. HOPS, I'll be talking more about this in the next slide. So this is a survey. It's called H2O Southern Galactic Plane Survey. It has been surveyed by Macarthur telescope, 22-meter dish. And it has measured all the, it has mapped the sky near our galactic center to both sides. So minus 70 degree galactic longitude to 30 degree galactic longitude. So 100 degree in galactic longitude, and the galactic latitude was plus minus 0.5 degrees, so 1 degree in total. And this is the longest survey so far I know about ammonia. And I have been working on the full stripe. So Cormac was working on it, and this is Andrew Walsh project. And this has been, it's called strip. So they stripped it in 11 different zones. So each of them are around 10 degree zone. But in the middle, which is the central molecular zone, because this can be very convoluted, it has got a lot of things going on in the middle, and we cannot really work on that for ammonia at the moment. So that is one zone, and there is another zone that has got no ammonia emission. So I'm stripping out one of this from here, and I'm showing it here. So this is ammonia emission lines that you can see, ammonia emission. So you see all these blobs and bright spots. These are all ammonia. So this is interstellar medium, and one of the, you can see this big clumpy zone, dense core, and this is a particular clump, we call it, which can form a star. And this is not from my survey data though, it's a Spitzer infrared data that I found from internet. So this is particularly showing this clump. How does it look like the molecular cloud? So yeah, as I was talking about Hub's survey, and we are using it so that we can find the dense cores, dense molecular zone where the stars are forming. And I'm using ammonia 1,1 transition and ammonia 2,2 transition lines that I was talking about before. So there are some sample images here that we found from Hubs, and they have got different molecular tracer you can see from here. This is methanol, and it's the same area of the sky. Just to show you, you cannot see the same sort of things going on in all the strips, though it's the same zone of the sky, right? So you can see how molecules can trace significant things that you want to look at. So this is quite, I can see it 0 degree. That means it's the central molecular zone. So at the center of the galaxy, which is really a lot of things going on. And you can see these three, so H3 is also showing a lot of dense core. These black patches are actually dense molecular cloud where the density is really high, and that can form stars. So this is ammonia 1,1 and 2,2. This is ammonia 9,9 transition. I'm not really working on that. So you have seen, if I'm working on this section, say, you can see that there is no star forming zones or dense cores here, but there are lots of dense core here. You can see that, right? It's already visual. But can you tell how many stars can form from this cloud? We cannot tell that because it's just a big bunch of dense cloud. That's all I know. How it is fragmented or how it is designed to be formed individual stars, or how many stars we can find. To find that, so you have got this dense cores. This is called dense cores. And there are lots of different space, so you can actually find them as, section them as clumps. That's called clump. Each of the zone that can form a different particular star, that's called clump. So I'm using clump finding algorithms. So I've been using different algorithms to find out which algorithm is the best one to find appropriate number of clumps in the dense molecular zone that can form stars. And I found that among all these 4 different algorithms, Fellwalker is the best one. Like clump find can give you a lot of clumps, but some of them can have 2 different clumps, but it's showing them as one single clump, which is wrong. Gauss clump is actually fitting Gaussian profile, and it can give you lots of clumps, which are furious, like those are not really real ones. Reinhold in the other end is giving you very less number of clumps, which are real clumps, but you are missing out a lot of clumps. But using Fellwalker, which I'm going to explain a bit later, this is the one can give you no fake detection, and all of the detection will be giving you the right number of star forming zones. So how is it working? It's a nice little plot here, right? Very colorful. So if you just think of this is a page of brightness, and this is a molecular cloud if you think of it, and this is the peak of the mountain is showing you how much brightness is there, how much ammonia concentration is there, if you try to understand like that. So this Fellwalker algorithm, you need to give a flat number or a cutoff number where it starts walking. Whenever it sees that, okay, there is something going up the value from whatever value has been set for the level, the background level, it starts walking. That's how it's Phil Walker. So it's walking up the hill, and whenever it finds that it's the hill, it starts going down. And kind of in this way, it traces out the whole clump here. And it can set that this is a different clump because the numbers you have given, or I have given there, it can tell that it is starting another different clump or not. And also, if something is like this, which is one single clump, it can also fix that as one single clump. Is this understandable? Too much?
Too clever computing.
Too clever computing, it's true.
Does the algorithm, that
Yeah.
algorithm that you're using,
Yeah.
does it work really well just with the ammonia or with other molecules as well?
Fantastic question. I haven't used it for anything else. I was using for ammonia particularly. But I have heard somebody else using it for another one. I didn't really know what the result came out. One of my another friend, Anita was using it. Yeah, I don't really know it. Yeah, but you can be using it. So this is, in fact, at the moment is still in beta version. So some astronomer found it and is still publishing their data and something like that. I think I'm one of the, I only know myself who has been using this method for finding clumps. Until today, everybody has been using clump find, which is another algorithm, because that's also good, but that can give you some fake detections. Or you can miss out some of the detections.
Did you start out using Clump Finder before you tried the others, or did you sort of go through a progression to get to Phil Walker, or did you see something in Phil Walker that you thought, oh, I'll try that one straight away?
So when I started doing it, that time Phil Walker just came in.
Okay.
And I have been suggested by Cormac Purcell that nobody has used Phil Walker before. And none of them has used it before either. They were saying there is something new came up. So he was asking Maria if your student wants to use it up or not. Now, there was nobody to help me out that time. Yeah, so I just played around with the computer and I tried to do one by one things. And then I figured out, why am I using Phil Walker? I need to have some particular reason for it. And then I tried out all different things and I was looking manually, checking manually, is it finding the right clumps or not, or is it false detection or not? So I laid out, and that's also a part of my first paper that I have been writing, that why Phil Walker has been chosen the best method for my work, yes. And I can suggest it for any astronomer actually. This is really good. Everybody, I went to Hawaii conference and I have seen people have been using clump find because that has been very authentic one. Yeah, very reliable one. But this is more reliable, I would be saying.
Someone's got a sense of humour considering the name.
Yes, hops.
Walking on the fell.
Walking in the fell, yeah. Yes, because he is walking up and then fell and then, yeah. Good jogger. So I think this is clear enough, right? So this is how I'm finding the clumps. So this is, when I'm talking about clumps, you understand that this is not the dense core. So you found that molecular cloud, and inside that you have got some dense molecular zone. And from dense cores or dense molecular zone, you have found clumps, which are candidate of star forming zone. Each of them can form one star. And I'm working on high mass stars. So now to show how does it look like when I'm doing it. So this pink, nice, elegant color, this stripe is actually from hops. I can just change the color, whatever color I want to display. So I used rainbow because I like that. And you can see these patchy colored are dense cores. And this one is with Phil Walker algorithm that it found the clumps, different clumps in. So it can give me up to 20 color, but this particular strip, I found 90 clumps. So it gave all the other colors as black, but still it gave the number of the clump that, okay, this is 1, this is 2, etc. So you can see this nice dense core. You cannot tell from here how many clumps you can find there. But you can clearly see there are 4 different colors: pink, magenta, red, and green. There are 4 different colors, and indeed they can form 4 different stars. So these are candidates still. I'm not saying that they are forming stars, but these are candidate zones.
Is that 4 different types of stars?
These are, I'm looking for massive stars. And why? Because these are all showing ammonia. Ammonia is good to find high mass stars or massive stars. The reason is high mass stars have got their critical density is really high. And ammonia's critical density is 10 to the power 4 centimeter cube. There are 10 to the power 4, that means 1,000 ammonia molecules you can find in 1 centimeter cube of gas. So, and that's particularly showing that if it can trigger, you can find ammonia, you can possibly find the zone where massive stars are forming. So now using that Fell-Walker algorithm, how many clumps I have found in the total 100-degree region? Well, I should tell that I actually avoided that plus minus 2-degree region, which is central molecular zone. Other than that, all the other regions, I have found total 500 clumps. So I can say there are 500 different zones or clumps which can possibly form high mass stars. And this is the sort of, so if you remember, ammonia looks like 5 fingers, the spectra. So this is one of the clump spectra, how does it look like? And then I fit it with model. So model fitting to show that what are the satellite lines and the main line look like. And some of the clumps, around 15 clumps, among all those 500 clumps, I have found they are showing really broad spectra. How does it, so it looks like this. This is also ammonia, but it's showing 1 finger here, 1 finger here. They're actually merging together. And there is 1 finger here, there's 1 finger here. So there are 5 fingers, but they're almost merging due to some physical reason. And here you can find just direct 5 fingers. So yeah, and I model them up. Of course, this modeling, I am not going to use all the data that I'm getting from it. So this modeling, so now I got clumps and I've got their spectra, and from modeling, I can tell what are their kinetic temperature. I can also tell what are their velocities because I've got the frequency there. And also a few other properties I can find from there. So with the kinetic temperature, how many clumps have got what temperature, and if you just plot it up, you see something like this. So the mean temperature is around 20 Kelvin, you can tell, for all my clumps, massive star formation clumps. Now, if you see this spike, I should talk about it. These are all showing 2.7 Kelvin, which is furious. It is not really the real one we want to know. The reason is, I was talking about those broad lines, and the model cannot really calculate the proper kinetic temperature for them. Because for kinetic temperature, you need to know the depth of the cloud, and that cannot be calculated if you don't have the satellite lines. So these are those. So, but these are not something that I want to throw out, because those are something I'm going to talk just in a moment. And also you can find the virial mass. So from kinetic temperature, you can use some nice equation. Equations are nice, no? Okay. Yeah. And then you can calculate the virial mass. It's nothing but the mass that has got gravitational potential enough that the kinetic energy is around half of that, which means it's gravitationally bound and it's not going to fragment or lose out its gases everywhere. Rather, it's going to form the stars. So that's why virial mass is very important. So we have got this VLSR, that the velocity I was talking about, that we can measure the velocity from the frequency. if you remember from the Doppler shift, and we have got this position. And if you plot them, you can see that there is something that is not there. It's because I didn't work on those clumps. This is the central molecular zone that I don't want to work, and I cannot really find any proper physical parameter from them anyway. But all the other, they have formed this warp-like thing, that velocity curvature you can see. But some of them, the red asterisks, you can see they are actually jumping around and have really high velocity. These are those with broad line. So it's really important. So we cannot really calculate their kinetic temperature because they are broad, but we can calculate their central velocity because we can calculate their central frequency. And this is something something new thing came up. I don't have that slide here, but I can talk about it. It looks like something like this. So say these are the clumps. Those clumps where those broad lines are showing, they're actually together. So I was going back, how do they look like? Are they together, or they have any particular information that I can get from them or not? And I found them. They are near so they are something like this, clump clusters, number one. Number two, you can see, they are actually near the center of the galaxy, not out that. Now, some astronomer called Ammonia, he also found some clump clusters like this, which is called Ammonia's clump, which is near the central molecular zone in 3.4 degree galactic longitude. But nobody has until now found these clusters, 1 cluster, 2 cluster, number 3 cluster. So these are my new findings. So hopefully I can name them as Shaila's clumps. I can be.
No.
Yeah. No? Yes? Okay. Yeah, my name will be there even if I die, isn't it? So something new came up, and so I'm writing this letter. Monthly notices, Royal Astronomical Society letter. I've been writing on that. And it's still going on. Hopefully I can finish that soon. Now, doing all these things, I started talking about you, big baby, secrets of starbirth, but I haven't really talked anything about star formation. I was still going on and going on and going on. This is basically my last slide. But what I'm going to do next. Until now, it has been very exciting, my project, but this is going to be more exciting because I'm going to find out more information about star formation. So this is an artist's expression. You can see the molecular cloud, dense core, or the clump, and that's falling in. That's called infall in our term. So the mass is falling inside that due to gravity, and it's also accreting some mass from outside. So that's infall. And also when it is forming, the mass it starts for forming, say it is having 100% mass, but it doesn't end up having a big star with 100% mass. It loses its mass due to jet or solar wind, stellar wind. So that's called outflow. And it's very important to know how much mass it was collecting, how much mass is actually going back to the ISM. All this information I'm going to know later on. So I'm going to model some of the modeling I was showing there, that's actually synthetic modeling, you can tell, or some calculation, but numerical modeling. But the modeling I'm going to do now, giving the actual parameters that, okay, if I have got this sort of mass, what mass would be the output, or what sort of turbulence will it have? So those sort of, if I have the density this much, what would be the physical parameters? So that would be my next thing to do. And that's going to tell me about star formation, how these stars are forming. So some of the information I'll be getting then. Yeah. So yeah, I would finish it up here. Thank you very much. Ask me lots of questions.